Any general questions, problems, anything? Hi, guys. Good morning. I'm sorry for the people on the Zoom. I'm laughing because there's only 2 people in the room today, so which is better than 1. There's nothing worse than being the only person in the room, because God forbid I ask a question and wait for an answer. It's a lot of pressure on you if you're the only person in the room. Any questions out there? Okay. We were talking again about really the precipitation side of the KSP, right? And it's not just an academic exercise. As we were saying at the end of class on Wednesday, right? I mean, the nature of doing chemistry is mixing stuff. A lot of times for synthetic reasons, you're trying to make some new compound. As some of you have discovered in your projects, if you didn't believe me when we talked about it before, right? The other reason you might do reactions is strictly to get energy, right? But in either case, right, the tendency as a chemist is to be mixing stuff in order to get a chemical reaction to occur, right? And so inherently, if the things I'm mixing happen to be salts, which again is just another word for an ionic compound, right? I can get cross reaction from any anion and any cation because they don't know who they are, right? If you're a cation, you sense the world, right, based almost strictly on your charge or your mass in the case of gravitational effects, right? But your physical properties determine how you sort of navigate your way through the world. And so, you know, the big defining characteristic of being an anion and a cation is the charge. And they're not selective, right? And so this idea of them possibly forming a precipitate is a real world problem. You can't very well get your aqueous reaction going if your reactants crash out of the solution as a solid. Right. We also mentioned, of course, the practical side of things, which is this is a common issue in the laboratory and outside of the laboratory because plumbing systems tend at some point to merge with other plumbing systems, right? And so any, again, ionic compound or salt that goes down the drain eventually gets mixed with everybody else's salts that go down the drain, right? And if they form an insoluble precipitate, they can actually form a very rock-like substance on the inside of plumbing, which actually over time reduces the cross-section of the plumbing, right? And then there are practical reasons why I might want to precipitate just for the sake of precipitating, right? That could be synthetic, right? But there's 2 common, virtually everyday applications of precipitation that's based strictly on the need to precipitate, right? And not necessarily based on any need for the precipitation itself chemically, right? And one of these is purification. This is a common problem if you have well water, although even if you have centralized city water, right? Some cities have harder water than others. And for people who are sensitive to it, right, you can get home purification systems, which generally mostly, I mean, there are some more advanced ones that are reverse osmosis or things like that, but a lot of them are based strictly on precipitation, right? Hard water is really just another term for a high metal ion concentration, right? And so one way to soften your water is to precipitate the metal ions out by adding some convenient anion And in fact, a lot of the home systems use hydroxide as a means of precipitating the metal ions that are in the water. And as we will be talking about shortly, this is also, well, I'm going to change tenses. This was also a very common way of separating metal ions. I think to some extent it's been largely replaced by electrochemical methods, but this was for much of modern human industrial history the most common way to actually separate metal ions from each other. And so you see this still in strip mining, although again, sometimes the final step is actually electrochemical instead of pure precipitation. But literally, if you ever want to see, one of the dirtiest sort of industrial chemical sites, look at what a strip mine looks like. One way to literally do it is to actually dissolve the mountain. Right? I mean, they literally run concentrated nitric acid or even mixed nitric and sulfuric acid down the side of a mountain. And those oxidizing acids dissolve virtually all metals. And so down at the bottom of the mountain, you get this pool of acidic metal solution that you could then precipitate the gold or the silver or whatever material you want out of it. And so this means of separation or purification is a legitimate application of my KSP, but again, in reverse precipitation mode as opposed to solubility mode, which is why at the very beginning of this, I said really the solubility part of it is the least interesting, right? You throw something in water, it dissolves or it doesn't, right? You might care, depending on what you're trying to do with that solution, how much you can dissolve, but that's not really a value you can move around, right? If you need, pick your favorite salt, sodium chloride and water, there's a solubility limit on how much you can dissolve. But if you need salt water, you just kind of have to live with it, right? On the other hand, if I'm precipitating it, especially if my goal is not to get a specific salt, but to get the metal out of the solution, I actually have options, right? I can pick some convenient precipitator that makes my life easier, right? The goal here is really to trigger the precipitation. And so this is again a case where I'm really mixing things, right? I don't just have a solution and just whatever happens, happens, right? It's more of a titration of sorts, right? And so, again, you would normally do this for silver or gold or something valuable, but here I have 500 milliliters of an iron nitrate solution, and I want the iron, right? And so one way to do that is to precipitate it. Now, again, technically I could precipitate it with anything I want for reasons we'll discuss later. I chose potassium carbonate to precipitate it. Right. And again, what is sometimes, to my mind, the tricky part of the KSP is it's always the thing I don't see that I care about, right? I've got iron nitrate here and I'm going to add potassium carbonate to it. I don't care about either one of those things. The iron nitrate's not going to do anything, right? I mean, it's dissolved. There's no reason for it to stop being dissolved. My potassium carbonate, I'm adding as a solid. It can dissolve, right? If it doesn't dissolve, I'm just sprinkling potassium carbonate around, and of what use is that, right? The reason I mix the two is not because I care about either one of them, but I care what might happen when I mix the two of them, right? And again, it boils down to my most important rule of all of Chem 2. If you have an ionic compound and it dissolves in water, it dissociates, right? And this is, I don't know, I lost count. Reason 4, 3, 4, 5, why that's an important rule. There's another one coming up in a couple weeks, right? Because again, technically speaking, I don't have any iron nitrate in the solution, right? Once it's dissolved, it dissociates, and it doesn't know it was ever iron nitrate. It's just iron ions and nitrate ions. And similarly, if I add the potassium carbonate, right, and it dissolves, it should dissociate, right? Now, again, we'll talk more about this later, but, you know, I mean, part of the reason I would add potassium carbonate is because, again, Chem 1 version of solubility, it's a potassium salt, it should be soluble, right? And once it dissolves, it dissociates. So again, what I have is 2 cations and 2 anions, and they can, quite frankly, pair up in any way possible, you know, much like my acid-base thing, right? Every acid reacts with every base because, you know, that's what acids do, right? Similarly, every cation reacts with every anion because that's what ions do, right? They stick to things that have opposite charges, right? And so, in theory, iron could combine with nitrate, potassium could react with carbonate, or they could change partners, and the iron sticks to the carbonate and the potassium sticks to the nitrate. All right. You know, and with acids and bases, I always said, look, if you've got, you know, 4 acid-base reactions, they all happen, right? Because that's the thing about acid-base reactions, you can't stop them, right? The one difference here is I have technically 4 Ksp reactions that could happen, right? But unlike the acids and bases, it's not automatic that they will happen, right? Because again, the one big difference with my Ksp versus virtually every other equilibrium we've talked about is that I can't always get to equilibrium, which is a fancy way of saying the reaction doesn't always happen, right? If I'm below the solubility for a salt, there is no reason for it to do anything except keep swimming around in the solution, right? And so, you know, there are 4 Ksps here, right? But the question really for all 4 of them is the equilibrium operating, right? Have I reached the threshold where the Ksp becomes an issue, right? And you could check them all, right? That's our old Q test, right? It's not until Q is greater than Ksp that precipitation happens. And so I can look up all the Ksps, I can calculate my QSPs. On the other hand, again, I know for a fact the 2 things I started with don't do anything. The iron nitrate was dissolved in solution. I haven't changed anything about it except adding potassium carbonate. You know, and here's a really deep thought. Potassium carbonate is neither iron nor nitrate, right? And so from the perspective of the iron nitrate, right, I haven't added any more iron or any more nitrate. I haven't even added any more water. I've done nothing to that equilibrium. So if it was dissolved, it stays dissolved, right? And the potassium carbonate, I'm just gradually adding anyway, and it's potassium salt. And I only added it because I knew it would dissolve. Otherwise, I don't have a reaction. right? And so the issue again becomes, what are the double replacement products that I could get? Because I do not know yet what the solubility of those two things are, right? If you want all of the KSPs, there they are. Right. And again, you know, as we suspect for such things, right, potassium salts and nitrate salts tend to be soluble. So, hey, that's a pretty big number. Potassium salts tend to be soluble. That's still a pretty big number. And nitrates tend to be soluble. So, hey, that's a pretty big number. Right. The only one that's a pretty small number is the iron carbonate. Now, again, if I throw enough stuff into my solution, at some point I reach the solubility limit for all of these, right? But again, remember what I'm essentially doing here is adding potassium carbonate, right? Which means my iron concentration and my nitrate concentration are already at their maximum. I'm not adding any more, right? But my goal is to trigger, right, one of these precipitations, right? Because I'm going to keep adding this until something happens. That's why I say to some extent it's something like a titration, right? The example we were playing with on Wednesday, I had just mixed two solutions together and said, what happens, right? In the case of an intentional precipitation like this, I am making it happen, right? And so I essentially start with no potassium and no carbonate, right? And so really all I've got is this, and this was happy, right? And so I'm going to start adding potassium carbonate, which makes any one of these three things possible, right? But again, you know, the old biggest K first, which becomes smallest KSP. As I'm adding the potassium carbonate, eventually I could add too much and it'll stop dissolving. Eventually I could add so much that the potassium nitrate starts precipitating. But as I'm adding it, the first thing that would reach its solubility limit is the iron carbonate, because it has by far the smallest KSP, which means lowest solubility. And so that also means essentially it has the largest K precipitation, right? Because again, I'm essentially doing this reaction backwards. Right. And so my first concern, and in this case, my only concern, because really my goal here was to get the iron, is how much potassium carbonate do I need to add to get the iron carbonate to precipitate, right? And so, you know, at some point there's a balance equation and an ice chart and a K equation, because of course it is an equilibrium and all equilibria have three parts, right? But again, because it's a KSP, I'm not always at equilibrium. And so really the first question, which is brand new and specific to KSP type equilibria, right, is really what is the threshold for my needing to care about the equilibrium, right? If I'm below the KSP, nothing happens, right? I only start to get precipitation if I exceed the KSP. And so that Q value, right, tells me where I am. And I really need Q to get up to K before I even have to start worrying about the solubility, right? And so in this case, again, since it's essentially a titration, right, I can add as much of the potassium carbonate as I want to make the precipitation happen, right? Or if you want to think in terms of the equilibrium, I can add as much potassium carbonate as I have to make the Ksp reaction relevant, right? And so somewhat unlike our other equilibria problems, right, there's really a threshold question here that does not really require me to have an ice chart or a K equation. Well, I need a K equation, but not as a way to solve the ice chart, right? My iron carbonate solubility reaction is iron carbonate dissociated into its respective ions. Again, I'm trying to get this to happen. And I'm trying to get this to happen by adding this, right? And so essentially my carbonate concentration is variable. It's not like I just have some carbonate in solution and I'm trying to decide what happens. I'm going to add as much carbonate as it takes to make something happen. Right. What's currently in solution is the iron and the nitrate, but of course the nitrate is not part of this particular reaction, right? And so I start with 0.022 molar iron, and I essentially have 0 carbonate. But again, I'm going to just keep adding carbonate until something happens. And when does something happen? Not until my Q, my concentrations of iron and carbonate, reach the maximum, which is the Ksp, right? And so how much is that? Well, as much as it takes for the Ksp to equal the product of the ions, right? Which in this case is not a lot because my iron carbonate is not terribly soluble. Right? I only need to add 1.4 times 10 to the minus 9 moles of carbonate per liter, which is not very much at all. In more normal sort of units, because it is a solid, right? That's, 96 nanograms. You need $1 million scale to weigh that out. Right? Which is why this will work. If I just take a scoop of carbonate, potassium carbonate, and throw it in there, I am going to grossly exceed the Ksp value, which is going to force the iron to start to precipitate. Yes, no, maybe. I'm going to complicate my problem in a second, so are we at least clear on what I did there and why? Chat people. I miss the applesauce days when I knew there were people out there. Well, the iron concentration does not change is the question. It does not change till you exceed, yes, I did say applesauce. And of course, that set off everyone. Yes, it's just like old times here in the chat. The iron does not do anything until you exceed the Ksp. At that point, when it starts to precipitate, the iron concentration will actually start dropping, right? Which is my goal here, right? If the goal is to precipitate the iron, right, I want it out of solution. I often make a graph here on the whiteboard, which is of no use. So hang on. I got to change my video settings so the people in the room can see the whiteboard. I'm going to miss all this technology when COVID ends. can have office hours in my office. Although sometime between now and then, somebody better clean my office because apparently FMS doesn't sweep offices anymore. So I have balls of dog hair all over the floor because I'm mostly a walking ball of dog hair on most days. All right, so if I really were to plot these things, I'm going to plot multiple concentrations on the y-axis, which is why I haven't particularly labeled them, but these are molarities. And if you want grams of potassium carbonate, I add. So, initially, when I've added nothing, there's 0 carbonate concentration. On the other hand, my iron was up here at 0.022. Right now, initially, if I start adding the carbonate, there's really no need for much of anything to happen, right, until this product hits the Ksp, right? And so, what was it, 1.6 times 10 to the minus 9 molar. I shouldn't put this arrow here, right? At that point, right, I've reached the maximum concentration of ions I can have for this equilibrium. If I keep adding potassium carbonate, right, this has to start decreasing, which allows this to keep increasing, right? Because again, in the end, right, from this point forward, the iron times the carbonate is always 3 times 10 to the minus 11. Whoops, don't talking right. Right, but I'm adding the carbonate. And so the carbonate goes up, forces the iron to go down. Or if you prefer, the iron going down allows the carbonate to go up. They're both happening simultaneously, right? And so this keeps dropping and this keeps gradually going up, right? At some point, you're essentially asymptotically approaching 0 for the iron. Right? And so, for lack of a better term, I can call this the pre-equilibrium, right? My iron and carbonate are below the solubility limit. When I hit that solubility limit, right, now my equilibrium starts mattering and I have to stay at equilibrium. And so any addition of the carbonate forces the iron to precipitate to stay at equilibrium. And if I add enough potassium carbonate, eventually, I get 99.99999% of the iron to precipitate, which was my goal, right? In practice here, because I only had iron, I really wouldn't do this as a titration, right? If I want the iron out, I'm just going to dump a scoopful of potassium carbonate in and all the iron's going to crash out. There's no need to do this gradually or carefully. Right. On the other hand, when I want to do it gradually and carefully is if I have more than one metal and I'm trying to separate them. Right. And that is really more the titration issue. Oh, come on. Right. And so this is more the separation issue, right? If I have two different metals or more present in my solution, I can separate them using the same basic procedure we were just talking about. But now I have two things I'm trying to separate. So I can't just take a shovel full of potassium carbonate and throw it in, because if I do that, I'm going to get both the iron and the magnesium simultaneously precipitating them. And so I haven't really separated them. I've turned them both into solid salts, right? But they're still mixed. On the other hand, if I'm more careful, right, in my additions of potassium carbonate, what I should see in somewhat similar fashion, right, is, I've got iron up here, I've got magnesium down here. Again, nothing should happen for a while until I hit the threshold for one of them. Which one? Well, you'll find out in a second, right? At that point, one of them should start precipitating. This should keep going up. The second one should not change until you exceed its solubility, right? And so initially, right, I've only got iron carbonate precipitating, the magnesium stays in solution. Eventually, I will get to the point, right, where they're both precipitating, because I will have crossed the solubility limit for the second salt, right? At that point, my effective precipitation of the first ion has ended, and I have a slightly dirty precipitation of the second ion that starts happening, right? But here's where my design in my precipitation makes this either effective or ineffective, right? If this is going to work, right, I need the iron, which is the first one to precipitate, to be 99.99%, precipitated before the magnesium starts to precipitate, right? Because now I've got virtually all of my iron out of the solution and drying over there, right? And my magnesium starts to precipitate, but because there's so little iron left, right, I'm going to get slightly dirty magnesium precipitating, but it's only slightly dirty, right? If the solubility is really, really close, this won't work at all, right? If this one starts precipitating here, right, I've still got, 80% of my iron in solution. I got 20% of my iron out pure, but I can't get the magnesium out at all because they're co-precipitating, right? But here's where my ability to choose the salt that I add, right, allows me to make this effective, right? Iron and magnesium can precipitate with virtually any anion I choose, right? What I want to do is choose an anion that has a big solubility difference. And so if you look at the Ksp for iron carbonate, magnesium carbonate, they're 100,000, a factor of 100,000 different. Right. If they were close together, I would choose a different salt, right? Potassium hydroxide or potassium chloride, right? But what I'm looking for is some iron salt and some magnesium salt, right, I can choose this piece where there's a significant difference in the Ksp so that they're not precipitating at the same concentration of the anion. Right. Again, they will precipitate in order of biggest K precipitation, which means smallest Ksp. And so for that reason, the iron carbonate, right, should precipitate first, and the magnesium should precipitate second. When does that happen? When I've added enough potassium carbonate to cross the Ksp, right? And so again, you know, there's an initial value for the magnesium, there's an initial value for the iron, right? The carbonate's initially 0, but I'm going to add as much as I need to make the equilibrium matter, or if you will, if you prefer, to start the precipitation, right? And so essentially what I have here are two thresholds for precipitation based on the amount of carbonate added. And I want those to be as far apart as possible, right? And that was my hope in choosing, right, the carbonate, because the Ksps are far enough apart that the thresholds for precipitation should be far apart, right? And so if I start adding carbonate, nothing happens until the carbonate concentration gets to 1.4 times 10 to the minus 9, right? At that point, I've reached the maximum amount of carbonate that my solution can tolerate, right? If I add any more, the iron carbonate is going to have to precipitate because I cannot exceed 3.07 times 10 to the minus 11 for the combined concentrations of the iron and carbonate, right? On the other hand, right, nothing happens to the magnesium until the carbonate concentration gets to 4.87 times 10 to the minus 4. Right. And so I do have a big gap between when the iron starts to precipitate and when the magnesium is going to start to precipitate. Yes, no, maybe. Now, in theory, I could calculate, right, how much iron carbonate precipitates for every little addition of carbonate, right? Because again, it's predictable. I could make a nice chart and solve it. On the other hand, I don't really care about what's happening every step of the way, right? I now have, let's see if I can squeeze this in here. Right, I now essentially have, whoops, multiple windows as opposed to the 2 I had before when I only had the iron. Right, so again, I'm adding potassium carbonate, and I'm going to add as much as I need to. And so here's my iron. Right. Here's my magnesium. And if I care, here's my carbonate. Right, so this is going to, go up. Right, so I still have essentially this pre-equilibrium period where everything's happily below the solubility and nothing's happening. Right. When the carbonate reaches that first threshold, which was 1.4 times 10 to the minus 9, right, I've now reached the maximum value for the iron and carbonate product, right? At that point, if I add any more potassium carbonate, it requires that there be a precipitation. And so I then have what's essentially the iron precipitation window, where this is going to start dropping. And during this whole period, the magnesium should stay constant. Whoops. Right. And again, I hope that most of the iron, right, drops out of solution before I reach the third window, right? I didn't mean for these lines to intersect, but, right, which was 5 times 10 to the minus 4, at which point I've now reached the maximum magnesium carbonate product, the Ksp of magnesium carbonate, right? At that point, the magnesium is going to start to precipitate, and then the carbonate keeps going up. Now I have too many lines. I should have changed colors, but right. And technically, this is still precipitating. Right. And so, if I wanted to do what I did with the titration, which is to calculate my titration curve for the KSP, I could, in theory, at any point along the way, pick, every 0.001 grams of potassium carbonate or some value like that, and I could do the precipitation and whatever, right? On the other hand, I don't really care, right? Because in this first window, nothing's happening, so, nothing to calculate. Here, there is something happening, right? But I don't really care what's happening in between, because my goal is to get as much of the iron as I can. Well, as much as I can, right, is the difference between these 2 points, right? Because my effective separation of the iron ends here. At this point, the magnesium starts precipitating, and because hopefully I chose my salt carefully for solubility, I should be mostly precipitating magnesium, right? And so any iron that's left there is really just an impurity in my magnesium, right? And so all I really care is what happened between here and here. So it's only really the endpoints of that frame that I care about, right? And frankly, if the magnesium is the only other metal present, right, then I only really care about, at this point, dump a shovel full of potassium carbonate in there and get all the magnesium out, right? If I had a third or a fourth or a fifth metal, right, I would get a fourth or a fifth or a sixth window, where in each window there should be one species that's predominantly precipitating, but there will always be a little bit of impurity from the things that precipitated before them, because the iron is never going to zero, right? Because you are at Ksp in this window. And so the iron times the carbonate is always 3 times 10 to the minus 11. And so the iron can never be 0. On the other hand, it can be close, right? Because the bigger the carbonate concentration is, the lower the iron concentration is, because it's the product that matters. It's not the individual concentration of anything, right? And so this calculation, or these two calculations, really are setting the parameters on my windows, right? Nothing happens. I'm all pre-equilibrium until I get to the first precipitation. And then the second precipitation starts at the second value, but that also effectively ends the first precipitation, right? At that point, the iron is still precipitating, right? But it's an impurity in what's predominantly a magnesium precipitation at that point, right? And so it pains me to even say it, right? I don't so much need an ice chart as I need to calculate what my concentrations are at the beginning and end of each of those windows, right? And so, you know, again, since I'm adding a solid in terms of grams, right, nothing happens until I get to 1.4 times 10 to the minus 9 molar, right, which corresponds to 9.6 times 10 to the minus 8 grams, right, given the total volume of the solution and the molar mass of the potassium carbonate, right? And so that's really the mass at this point, right? That defines the beginning of the window, right? The second calculation defines the end of that window, right? I start to be magnesium instead of iron when I get to 4.87 times 10 to the minus 4, right? But here's the thing. I can't get to this carbonate concentration unless the iron carbonate equilibrium lets me, right? What does that mean? It means the iron has to be low enough to where it's, I'm going to go with legal, right? The iron concentration has to be low enough to where it's legal for the carbonate to have risen to 4.87 times 10 to the minus 4. And so I don't really need an ice chart to know how much iron is still in solution at that point, right? I can only have this concentration of carbonate if the iron has gotten low enough, because once I've hit that first window, the Ksp of the iron carbonate stays in effect. Right. Once I've triggered the equilibrium, right, it stays in effect no matter how much potassium carbonate I add. Right. And so wrapping that up quickly, right, my iron dropped from 0.022 to 6.3 times 10 to the minus 8. Whoops. Right. So in other words, at this point, I've got roughly 3 times 10 to the minus 4% left, right? Or in other words, 100 minus that, 99.9997% precipitated, right? That's what I want in an effective precipitation. I got 99.9997% of the iron out. After that point, I'm mostly getting magnesium. It's a little dirty because of the iron, right? But there's so little iron left. The magnesium is also going to be 99.99% pure, right? And so I then have effectively separated my iron as a salt and my magnesium as a salt, and I now have iron in one beaker and magnesium in another. Questions on that? Problems? Anything? Then we will wrap up.
I have a question in the chat.
KSP on Monday and get to thermodynamics, which is really where we should have started.